Consider this part 3 of the monitor unit equation breakdown. This one I want to concentrate. This goes in with a wedge factor and an off-axis factor, and it involves talking about beam profile. The physicists, when they do not their calibration, but their modeling of the beam, okay, they sit down for a weekend or 40 hours or so, and they scan the beam. They scan depth doses, vertically along the beam, and then they also scan in-plane and cross-plane profiles. Cross-plane profiles would be left to right, looking at the gantry. In-plane would be like in and out in the couch direction. Okay, and they put all this along with the field-dependent dose rates into the treatment planning computer, and then it allows the planning computer to model the radiation beams in virtual reality. So we need to talk about beam profiles. If I have a radiation beam, this is my treatment head up here, radiation beam coming down. If I scan across the beam from left to right, that's what I'm talking about when we mean beam profiles. Okay. Now if I were to graphically represent this, how would this look? How would this look? What we have is I'm going to draw for a 10 by 10 field size. And we have some specific parts of this profile. We have here, we call these the tails. There's always going to be some radiation present. There's leakage from the treatment head, and then there's also scatter radiation from inside the beam that's always going to give us these little asymptotes that go out. All right, we get a curvature up. Notice that it's not a straight line. It doesn't go straight up, straight over, straight down. The beam does not look like that. Okay, we're limited to the laws of physics. We curve up. I come up over a shoulder, dip down in the center, come back up to a shoulder, and I get the same thing on the other side if our beam is symmetric and flat. Okay. Now, the different parts to this are I have 100% is on the central axis. Everything's normalized to the central axis. Okay, and these are the different parts of my beam profile. I have what's called the full width half max, which is going to be my 50% isodos line. Okay, my 50% level. That corresponds to the light field. The light field in the treatment machine dictates the 50% isodos line. I have 20% is another magic number, and 80% is another magic number. Now, the region going from 20 to 80% is called the penumbra. Most manufacturers are going to specify the penumbra as the 20% to 80% line. In Khan, you'll read it that it's either 20 to 80 or 90 to 10, but most people use 20 to 80 because it's a smaller width than 90 to 10, and it makes your machine seem like it has a tighter beam. So when you talk about the tightness of the beam, okay, the tightness of the beam is how small is the penumbra, because the penumbra represents the fuzziness of the beam, the fuzzy edge of the beam. If your physicists do monthly QA, and if they still use film for a radiation light field check, I would encourage you to look at the film. The film will not show just a black square. There will be a slight fuzziness to the edge, and if you put it on the light box, you will be able to see that. And the fuzziness that you're seeing is this penumbra. Again, 50% isodos line represents the light field or field size definition. These up here we call horns, and they vary in size depending on the energy that you use and the depth that you're at. And the horns are caused by the flattening filter of the beam. We can hopefully discuss that at a later time, why that's the case. But they will be there at shallow depths, and they will not be there at deeper depths. Okay? Most machines are designed to have their flatness and symmetry specified at a depth. Whether that's Dmax or 10, most of the time it's 10, since most treatments are, I shouldn't say most treatments are 10 centimeter depth, but most treatments are at depth rather than Dmax, so they make it flat at 10 centimeters. The flatness of the beam is going to be defined by your maximum point divided by the minimum point. That's your flatness. The symmetry of the beam is if I pick a point here and an exact point on the opposite side from the central axis and I divide those two, that's my symmetry of the beam. The beams need to have a specified flatness and symmetry. You can ask your physicist to talk to you more about that. What happens when I put a beam modifying device in the field? What happens if I put a wedge in the field? How does that affect my beam profile? So now, if I draw a beam profile, I'm running out of room, and I put a wedge like this in the field, what does my beam profile look like? Remember, everything's normalized to 100% on the central axis. So I still get my penumbra, I still get my tails. Under the toe of the wedge, I get increased radiation because I get less attenuation, thinner part of the wedge. I get 100% at the central axis, okay? And then I get less radiation under the heel of the wedge. I still have penumbra, I still have tails, everything's normalized at 100%, but now I am over 100% under the toe, and I am below 100% on the heel. How much those percentages are depend on the type of wedge that we put in. This is going to be greater for a higher wedge angle, meaning like a 60-degree wedge, but it would be less than if we used a 15-degree wedge. The same case happens for enhanced dynamic wedges or virtual wedges. If we use a 15-degree wedge, roughly, as we go away